Yeah. Okay, so I set a root to 0.1 in order to easily see the difference between r and r squared and r to the power 3. I don't think the other two roots matter much, so I just take some random value, having, I don't know, I think whole numbers here is not what you want. Pick a C3 in case that matters as well, and then we calculate the coefficients of the polynomial using the roots. I start with all epsilons at 0. And I have a function that evaluates the cubic according to C description, namely this. It's also given in the description, but using a precision of 256 bits. So, yeah, not doubles. And this is a root, right? So if you evaluate it with all 0 epsilons, then the result should be 0. That's the definition of a root, and it is. This prints 0. Now we introduce a small xi, which is set to 100 millionth, and use that as an offset relative to this root, and then evaluate it again. And then of course you get something that is not 0. However, this is our f of xn. Xn is equal to r plus xi, so yeah. And now we introduce an epsilon. It's at epsilon 0 equal to 10 to the power minus 18. If now you evaluate this cubic, getting an error on YouTube. What the fuck? Does it mean that we're not live anymore, or? Okay, so I set epsilon, only epsilon 0, and then we have an approximation of f at xn using this epsilon, and then we can get the error term of that. So all in all, this prints. No, you see, the root is a Supermachio root. This is then the f of xn, and this is the f of xn with epsilon equals 10 to the power minus 18, and the difference is this. So this is our error term, and now the question is, how does this thing relate to epsilon 0 and the rest? Assuming it has a form like this, to this in this case. There's no epsilon 0 here, but suppose there was an epsilon 0. Well, I think it derived somewhere that yeah, Claude is just not doing nonsense all the time. Well, it's summarizing what I say. Not even in a bad way, but I'm doing all the work, unfortunately. Sorry, I say that the result should be epsilon 0 times C0. That should be the error term. So we can find this C0 now by taking the derivative with respect to epsilon 0 of the error term. And that the result of that then should be equal to C0. So I want to have the derivative. Now, how can we calculate that? I first have to calculate. Well, I have to set this to a different value. I'm going to add. So we add a delta simply. So I make a delta here. Delta. That should be significantly smaller than epsilon, obviously. It's really small. But we have a really accurate calculation here, so maybe 30? It's a bit too small. Yeah, just a lot less than a millionth of this is not necessary, guys. I choose 29, or even more, 28. What did I say? The other way around. Do it differently. Just 1/10,000th of E0, and then we add that, and then we evaluate that again. So now we get, let's call this 2. The new evaluation with the different epsilon. And then we can calculate the error of that. A minute. And let's print that as well. Let's see if that difference is still having a lot of precision. Oh yeah. So all of this still stuff that we have to work with, which is logical because it's about one. The error in the error is about one. Well, the difference in the error is about 1/10,000th. So can definitely get more accuracy, I think, by dividing it by a million. So you have plenty of accuracy there. Okay, there now we can calculate the derivative. With respect to epsilon 0, let's just also do d, the dE0. That's the derivative with respect to E0. No, that's not how I did it. And this is df d epsilon 0. which then can be calculated as see the difference between the error values divided by delta, right? Well, delta is positive and the error 2 is larger, then this gives a positive derivative, which is then of course correct because it increased. No, that is clear, I would say. That is that value. Down to infinite precision. Holy moly, this part is different. The rest is the same. So pretty safe to say that it is that value. That is the f of xn. I had not expected this. It's not what I expected at all. I expected to get this. Oh wait, this is what you, if you said C1, C2 and C3 to 0 as well. In which case C0 is equal to the fxn. So yes, ta-da. We compare that to this. So we can now write that in this form. Let me copy this. Okay, there's no epsilon 0 here, so let's ignore all of this. And now it turns out that we get the fxn times epsilon 0. Just type E0. Yes, the partial derivative of this term, partial derivative of the error, so that is this minus that, so that is all of that, with respect to E0, which means that we can ignore all of that, we just take the partial derivative with respect to epsilon 0, equals that. Therefore, this is how the error depends on epsilon 0. And then we can fill in this, because that is the mathematically exact formula. which is I think I gave that, I'll have that here as well. This is approximation. I didn't add the A yet. No, the real value is simply maybe don't have it here. I don't have it here. Do I have it here? I'm going to reload this page. See what happens. Yeah, it works. Okay, I think I have it in the description of the video, so let me have a look there. Yeah, see, there it is. F of x is, well, this is that, of course. The f of xn is simply, I didn't write that down. No, but you can, oops, I can just copy this one. This one, yep. So the f of x is that, so the f of the derivative turned out to be, for possibly a new viewer, so the derivative turned out to be basically the same as this, which is the f of xn. Down to, well, all the way up till here. It's unbelievable. Match, match. Thus, the derivative relative to epsilon 0. So this is the f of xn. And we can get that then by multiplying, well, by filling in xn for the x here. So now we have the correct formula. And then we can distribute that again over these terms. So I'm going to no, I'm gonna leave it like this at the moment. Let's leave it like this. No, let's not leave it like this. Let's fill it in. Okay, so this is, I'm gonna pretend that, well, all the epsilon 1s and 2s and 3s and 4s and 5s are not correct. Maybe not correct. But I'm going to leave them like the way they are. But I want to have a plus sign here. So I'll make this a plus and this becomes a minus. And this is a plus. I'll make this a minus. Times that or something. And this is already plus. And I want to merge in this. So I have a C0 here. And the C0 is multiplied with epsilon 0. And that would be a plus. So there is an epsilon 0 here. Possibly. And then here we have a problem. Of course, this also has a C0 in it, so no, I should not have done that. Nope. This part here is here, 2 times epsilon 0. There comes an epsilon 0 here. Plus epsilon 0 times that one. And then the last one is that, yes. So now I have epsilon 0 times C0, that was this one, and an epsilon 0 times C1 xn, that is epsilon 0 times C1 xn, and an epsilon 0 times, oh, there's a C2 missing. Epsilon 0 times C2 times xn squared plus C0 times C3 times xn cubed. Yep. So now we put it in this part. And that didn't really follow from it yet. So what we really have is now I'm having epsilon 0 all over the place again. Might as well I think I'm going to write this just as C1 times that. And then we need an epsilon 0 here as well. And the rest is then unknown. Other epsilons. I guess there should have been an epsilon. I'm just going to delete this. Oh, I'm going to derive it anyway. Now I recognized by eyesight that these two were equal. But what if I had not recognized that? Then what would have been the way to proceed here? Well, we have I should have split this thing up into all these different terms, right? These terms. And I think that yeah. That isn't that easy, is it? You can of course set C1 and C2 and C3 to 0. That is correct, that we could do that. But I'm not 100% sure then that we still find what we want to find, because then we don't even have a cubic anymore. I think it would be better to I mean, I want to know if it is, let's say, yeah, damn it. I'm having the feeling that it stays this way, right? I mean, C1 is always multiplied with xn, and C2 is always multiplied with xn squared, and C3 with that. So we take the partial derivative with respect to, say, C2, then the rest, whatever it is, stays the same. And if then we subtract that from the previous one, then we end up with only this term. So I mean I have to take the twice a partial derivative. First partial derivative with respect to C2, and then the partial derivative with respect to epsilon 0. If you do that, then we should get this xn squared, where xn is 0.1, so then we get well, the fact that we get 0.01 then means that it is plus 1 times epsilon 0. If we would get minus 0.01, then it would be minus epsilon 0. And we get, 2 times, 3 times, minus 5 times, whatever. So we can get this factor by taking the partial derivative with respect to C2 and E0. And then the same thing for C1 and C3 and C0. And then we get all these factors, and then we can do that for the other epsilons as well. Yeah, that's the way. The question, however, is how can I take the partial derivative of two of them? Because this is just the difference divided by the delta, but then how do you do that for the other one? Maybe that is a question for the AI. Might know that. It's a simple enough question. I just don't. Let's start a new chat. So, if I have a multivariate function, I don't know. I have a function of multiple variables. Wait a minute. That's sigma. I need a delta. It's the only delta I see, but it's not the right delta. Where's my delta? Oh, here it is. This one. The round delta. So we want to calculate the partial derivative with respect to of f. With respect to a, whatever. And then the partial derivative of that with respect to b. What's with the weird claw? Whatever. Yep. No, that is correct. Let's implement that. Let's replace A with 0. I don't know, I feel like first taking the derivative with respect to C actually. Let's say C2. Go ahead, any example above. And then let's say we want to replace B with epsilon 0. This becomes a B, this becomes, well, E0. Oops. So in order to calculate this, we have to set we have to add delta to C, so C2. So C2 plus is delta, can use the same delta or different delta, doesn't matter much. And then we have to evaluate that thing, so let's call it imperial. I numbered it with 2 here, there must be a better way, right? It is an approximation at xn with a delta applied to E0 and C2. I'm gonna do delta C2 delta E0. Which is just then the evaluation of that thing. Right, so we already had this one, and here we have this one, which I'm gonna rename now to xn, the delta E0. So that is this one. So this is this one. This one is this one. This one is the last one, and we only need this one. So I just need to reset E0 to what it was. I'm just going to do that again, I think. So I hate it that everywhere I'm using epsilon, and then suddenly I switch to E, because I have to use E in the code. Oh, to be honest, I don't see an. Oh yeah, here's an epsilon. See? There's only one epsilon. Still, in the comments, I'm gonna call it epsilon, I think. Substitute E0 becomes epsilon 0. Oh. What? Nothing happened. Undo, redo. Wanted to do that here. Substitute. I think I just typed E0. Yeah, we want to use epsilon 0 here. That's better. And here as well. That's this thing. Is hence with something divided by delta. Where something is some difference divided by delta minus some other difference divided by delta. Might as well move that outside and divide it by delta squared. Is that not true? So I'm going to use util square the delta. And then here we get this one with the double thing. Minus this one with just the DE, that one. Minus this one, so that is minus the other one with just one delta. That's the last one. And then plus the normal one, which is this one. Just write it out here as well. Brilliant. I love it. So this is 100th, which is the square of 0.1. And yeah, that's it. I mean, I can divide this by the square of 0.1 and then we get 1. So that is then the factor of the epsilon 0. Yeah. So we can find a thousandth if we do the same thing with C3. So the wonder we cannot do all of it. We probably. If you want to completely automate this, I would have to loop over all epsilons and over all C's. And then once we have this, figure out which term it is. This one, this one, this one, or this one. And then store the the factors of all those epsilons somehow. Which are extremely likely integers, by the way. So the position that we got here is pretty cool. Well, pretty good, I think. There's 1, 2, 3, 1, 2, 3, 4, 5, 6 zeros. Maybe it has to do with the Xi value. I'm not sure where it comes from. I mean, this is clearly noise, right? So that's round off error stuff. But the 2 and the 1 here, what does that mean? That doesn't look like noise, actually. Oh, that is, I think that's indeed, that's just a double factor of, so Xi times epsilon or something like that. Which I want to ignore, but it's not really ignorable if you go to two large positions. But yeah, I am only interested in recognizing an integer probably not larger than 3. Plus or minus maybe, and up till 1000. So we can easily recognize this thing as being 1 times 100th. Or for example, we could get a minus 0.003. That would be minus 3 times 1000. Yep, let's just do everything in a loop. Okay. So here we can recognize that the derivative, and this derivative is dfd epsilon 0 equals, well, the f of, so this one, but I'm just gonna write x in here. So now each of these is simply the sum over all epsilons. So we need a sigma. Oh, fuck. Control top. What the hell happened here? Oh, cancel. I'm not having a sigma here, really. Nope. Sigma. Mathematical bolt. I don't need bolts. This is mathematical bolt. Why is the word mathematical only mentioned when it is bold? Or italic? I'm just gonna go with this one. So we do the sum over all epsilons, which we done with some factor in front of it. So No, yeah, let's call them alpha. I mean, I don't know, why not? Let's pick alpha. Oops. So you have an alpha, and then we have two indices, I and j. Multiplied this thing with epsilon I. So that would be this, yep, the whole thing. Just each of those epsilons gets some integer in front of it. And then all of that is multiplied with, well, actually it's multiplied with C0 here, but I already introduced the J here, so might as well go ahead and use J there. So this is Cj. Where's my J? Here's a J. Times xn to the power j. Yeah, so here it is times 1, so that's to the power 0, and here it is just xn, so it's to the power 1. And here we have c2 times xn to the power 2 and c3 times xn to the power 3, so it's just this to the power j. And now of course we don't have an upper. It's really so bad of the UTF, of the how is it called? I'll show you that. Superscript, I mean, superscript. I mean, for some reason they decided not to include the whole alphabet, just this. Why? What the fuck? I mean, how do we need this, but not... Oh, we have an I. We don't have a J. I mean, hello? There is a B also? No. I think we are just lucky that they included all digits. So kind of ridiculous. Yeah, that's what I meant. Yeah, Unicode. Unicode does not have superscripts for the whole alphabet. Why? Nah, come on, it's impossible. The N must exist. N? Oh, okay, there's an N here. Superscript N. No, we're gonna use N because that's the only thing we have. N. This must be N to the power N, and then the J must become N. So, like that. Oh wait, I already used an N. No, different N. Different N. Everyone sees that it's different N because the font is different. Cry. No, seriously? There's another option? Not really. We have an... I only have N here, really. Superscript. There are more superscripts though. A few more, maybe. Could use A? Yeah, no. C? Nah. I could swap the A, the I and the J. Could use I for the... Yeah, maybe I should do that. Okay, I'm going to use I. Unbelievable. So this becomes J, this becomes J, and then this becomes the I. Oops, the other I. And then here we have to the power I. No, yep, I. Now we have a J. J, J. Okay. I need another sigma. So this sigma runs over all J then. I don't have an J like that, so I just use a normal J, I suppose. And then in front of this you need another sigma. Runs over all I's. Let's add another. Yep, and we want to find all the alphas, yes? So that's a double array. To do standard array. Or standard array, very nice. Do you have no double subscripts? And then the first one is going to apply on the outer one. So this one is the one that has the I as index, I think, and this one has the J as index, which happens to be the same order. Yay. I'm going to store integers, probably, which let's add an assert to make sure that it is an integer when calculating it, but yeah, it has to be integers. So, and so the size of J is the number of epsilons, so that is the same as the size of E, the number of epsilons, and then the I runs over all the powers of that thing, so that it runs from 0 to 3. But, well, 0 up till and including 3, so it must be 4, which is then actually equal to the number of coefficients, obviously. And this would be ij. Yes, because the first I applies, of course, on the array that it is, which is this one, which is the coefficients. So I is the number of coefficients, which is literally the number of coefficients here. The coefficients are indexed with that. And the power of xn. And then the other one applies to the epsilons. Hence the size of epsilons is equal to that. And then we're going to calculate that as, now we can, well, C was using I, so I just use C here. Wait a minute, I probably should do that like this. Substitute subscript 2 with subscript I everywhere, and then substitute subscript 0 with subscript J. Now we want to fill this whole thing, so we have to run over all I and all J. Order doesn't really matter. For now, I'm just going to print And here too, it is CI. Substitute C2 becomes CI. Oh, that was good. Then again, and we do E0 becomes epsilon J. Yeah. I already use stuff in front of it. I use this one and this one, so that's not going to work. Let's recalculate them. Is that nonsense? Let's see. Epsilon 0 Z. Only epsilon 0 Z here. Oh my god. It's suddenly a tiny little bit more complex than I thought. No, that doesn't matter. But yeah, I probably should just calculate everything. So also these two. Again, I just do that here inside the loop. So we begin again by setting epsilon J. Really, this is J. Yep. Okay. I want to reset actually before we enter this loop. What did I set? Only epsilon 0. I said epsilon 0. Yeah, this is like the first thing that I'm going to set, I think. So maybe no need to reset that. No, it's not true. It's being set here. Wait a minute. Huh? Oh no, here, this one. I already added delta, so that's not a good thing. Let's just reset it at the start before we enter. No, that also doesn't make sense, sorry. I have to override everything. Reset everything. I'm just gonna set it to 0. So everything was 0. So now the whole E array is again 0. And I don't think I have touched the coefficients yet, so we're fine now. And then we enter the loop. And let's begin with calculating the last one. So that would be NP real, and that is then called FAXN without the deltas. and that is of course always this. And in front of that, then we need an epsilon. We need epsilon j. So ej is imperial. E minus 18. That's what I was using. Yep. So the coefficients are already set, they're just the cubic, and the epsilons are all 0 except for ej now. And I don't think it really matters. I could set the others on as well, but then why not set them to 0? Okay, and then if we increase the coefficient I with delta, wait a minute, gee, that's not good. What we did outside before is increasing this with delta. And then we get this one with the delta epsilon j. And then we increase also the coefficient I, so then we get this one. And then I reset epsilon j. It's kind of the same as here. So now we have just the delta of the coefficient. And then we have all 4 of them, right? 1, 2, 3, 4. So then we can calculate the derivative. The double partial derivative. Which we can print then. Try to compile that and see if that indeed looks like 0.1 to the power something all the time. Huh? No j, no j. Oh, okay, well. I love it. I love it. So if you ignore everything down here, then it's just thousands or 0 or 100th or 1/10. There is one that is 1 actually. Or 1, yeah, that is 0.1 to the power 0. Brilliant. We can even investigate this by converting it to a double first. No need to work with all this noise. So yeah, it looks almost too simple. I had expected it's only +1. Every time it's +1. 0 or +1. It's never 2 or 3. Ridiculous. Yeah, okay. Yeah, I'm hardly motivated now to write full code that would extract something else. No, why not? Let me try how fast I can do that. So extract alpha, and we do that by starting with a double, which is a double derivative that we have, which we just get from this imperial to double. So you can print that as well. But we know that everything is an integer, apart from a factor of 1000. So in fact, I would rather work with an integer. And then we multiply this 1000. So, and then we have to still do a round off maybe before taking the floor. So I don't want to take the floor, I do a round. Yep. So 1000 now means 1. And this is a tenth, etc. So if you take the log 10 of this, then you get well, this refers to coefficient 0, and this one refers to coefficient 3. So we can take the log 10 of this and then do 3 minus that. But unless when it is 0, I don't have to do, then it is 0. Well, I can't take the log 10 of 0. So if it is non-zero, if dd is not 0, then we can do something with it. And then I want to get the factor. I just might as well dump it in here directly, I think. So this would be like 3 minus the 3 minus the log 10 of dd, I think. No, that's not true. That would be the index. Sorry, this is the index of the coefficient. Sorry, it's like this. The index of the coefficient is given by how many powers of 0.1 we detect. And then, what is the other coefficient? That would be j, which is the epsilon. That's epsilon that we're working with, but that would be just j. Yeah, in all cases it's just 1. It's kind of annoying, but that's what we see. So I'll just add an assert here that makes sure that that is the case. So dd is 1, or dd equals 10, or dd equals 100, or dd equals 1000. Turns out to be one of these, meaning that alpha is 1. Let's see if that compiles. It does. Now I want to print it. So after this, we print the result, namely that the approximation, the approximation is equal to the exact value plus and then we get this shit. Let's copy that because it doesn't fit on my screen. At the same time I have to code it. So the outer loop starts when I run int I from 0. Okay, let's use the same thing as here. Might as well copy it then. stuff. Okay, let's see. So this loop here prints this. But only the stuff that repeats. So that kind of depends on how many things we printed, whether or not we need the parentheses. Blah. Just write it to an output string stream. And then the whatever code. So now we really start to print. Okay, kan ik goed gedaan. That was a better way to do that, printing from a string, but nah, something with rdbuff or something. I don't want to be bothered with it right now. So this prints whatever is here with or without parents, and now we have to multiply that with this part. So I think that's always there. I just print that beautiful dot that we have here, and the C. And now we need the subscript I. Okay, let's not print the subscripts. You can also exaggerate. Let's just print I. And then we also always print, no I don't, wait a minute. And then if I is larger than 0, then we have to print dot x in. And if I is larger than 1, we even print the power of I to the power of I. So now we printed all of this. I think so, yeah. Didn't we? Where's my I then? I. Okay, now we get to the end of the I loop. So I guess here, if I is less than the size of C minus 1, we get a new term, in which case we need a plus. But if I remove the plus here, then we don't need to do that. And we just always print the plus here. Way better. Now this part. So this would now print everything without parentheses, which is just the alpha times epsilons. But the alpha is always 1 or 0. So it kind of depends on if alpha is set at all. So if alpha ij, then we print the epsilon value. I'm gonna make it an E in this case, I think. What is E? J. J is the epsilon value. And I want to know if we already printed something. If we have, if you have nothing at all, well, that's not going to happen. Okay, let's say so epsilon is false. So if we have any alpha that is non-zero, then we did see an epsilon. And if we saw epsilon before we saw this epsilon, now we need a plus and parentheses. So I need parentheses true. But I can move that in front of it. Because if we already saw an epsilon, then we, like I said, we need a plus. And then that's an afterthought, maybe the parents need to be set. I think it might be pretty close to this. Let's just try it out. It's all big formula and no parentheses printed here. What? Oh, because I'm not printing to the output string. You idiot. I feel a bit disappointed here. All of them times C0. All of them except E3. What? Times C1. All of them except E2 and E5 times C2. And again all of them. Shocking. Is this correct? Is the question. So epsilon 3. There's no influence on this. Why would that be? I mean, I just wanted to be correct. In the end, it doesn't really matter much. So each of these epsilons are, by lack of, how do you call that? It's like entropy thing. non-deterministic-ish thing, or just non-calculatable. I mean, they are highly correlated, but we don't know how. So it just disappears in the fog, as it were. And as a result, we just approximate it with pure statistics, where each of these are uniformly distributed things that are independent, but they're not really. But we don't understand how that works anyway. So a good approximation is to assume that they're independent. And if you add like 5 independent uniform distributed uniform distributed between the plus and minus machine alpha, then machine epsilon, sorry. Now you get something that is starting to look like a normal distribution. I think the sigma is kind of related to the number that you add. I mean, it gets wider, so if you add more of them. So apparently, in that sense, you could say that the influence is slightly less of this factor, because it has only 4 epsilons, and this one has 6. But yeah, I mean, come on, it's not really big difference. Huh? So in the end, I would say that it seems like that each term in the cubic, it just introduces an error. I mean, a linear with the absolute value of it. Interesting in itself. Someone said, aren't you participating in Advent of Code this time? Well, yeah, I started with it, but I did it only 2 days, and in which time I coded 5 days of them, and then I lost interest again. Oh, that was an hour ago. Well, guess he left. I think it's time for me to go shopping. It's in 3/4 of an hour the shop closes. I don't have breakfast for tomorrow. I wish I could wrap my head around why the E3 is not appearing here. Okay, so to summarize, what I did is I kind of assumed that if you, I'll summarize it, incompleteness. Like we have this formula. Well, we want to calculate the cubic, and I'm going to do that by taking a coefficient. You begin here, I guess. You take coefficient 3 and multiply that with x. And then we add coefficient 2. And the result of that is multiplied with x again. And then we add C1, and then we multiply it with x again. And then we add C0. Yeah, and that's the way you calculate a cubic. But every time you do an operation like that, there is a a possible round-off error happening, meaning that you have to multiply the result, and this result is calculated with 256 precision, so it is way more precise than a double, these calculations. So I just consider them infinite precise, and so I just multiply this with 1 plus an epsilon, where the epsilon must be viewed as a random distribution, yeah, because the round-off error that happens means you just cut off after the 51st bit significance, and it's kind of digital noise by those least significant bits. So noise, you don't know what it is, but it is exactly between what fits under the least significant bit. So it's uniformly distributed over the remaining bits. So every time we do an operation like multiplication and multiply with that, and addition, same thing, and so on. And then you get an insane big formula. If you would write this out, it's absolutely not printable. But we are assuming that every term where you multiply an epsilon with an epsilon, you can ignore that. And since I'm trying to approximate the root of a cubic with Halley's method or Newton-Raphson, for example, and I'm interested in why it stops getting more accurate. So that would be in the end. So we are already close to the root of a cubic, and we approximate that with taking the root and then saying xn is equal to the actual root plus a small value. So we are very close here. Just 10 to the power minus 8 away from the real root, and the real root is 0.1. So I set that to 0.1. So we're just a 10 millionth away from that, from the real root. And then if you apply Newton-Raphson or Halley's method, then how do the floating point round-off errors influence the result? And I'm starting here with just calculating the cubic itself. And then you can say that it's something like this. Yeah? So it is the approximated value with the floating point round-off errors is equal to the exact value plus the epsilons, because we don't have epsilon times epsilon, and we don't have epsilon times xi, where xi is the distance between this value and the actual root. So it must be just epsilon and so on. Yeah, just epsilon 0 or just epsilon 1, and then multiplied by C0. Now it turns out, kind of, in my mathematical attempts to derive this, that the formula is this form. It's just a series of epsilons times C0, and then the same times that, and the same times that, and so on. And then in order to determine the factors in front of each of these epsilons, we calculate the partial derivative with respect to one of the coefficients, for example C2. And then what you get with xn being more or less 0.1, you get 100 times this thing. And then we take the partial derivative again, and then you get 100th times this vector. Now I think about it, here I'm not really caring about what it is, but it's not what I should do. If we take the partial derivative relative to Ci, then I know in advance what dd should be. So in this case it should be equal to the power of 10 to the power, see the opposite of what I do here, right? So that is 3 minus, we think. So if I is 0, then this should be 1000. So it is 3 minus I. Yep. Now, because you simply, if you take, if this formula is correct, then the partial derivative with respect to C2 must be something times 0.1 squared. And then if you take the partial derivative with respect to one of the epsilons, then again, and the factor turns out to be 1 all the time, then it's going to be exactly 0.1 to the power, whatever the index is. Let's see if this indeed doesn't assert. No, so that works. So all of these all of the factors here in front of every epsilon is determined by first taking the partial derivative with respect to C1, and then all of this drops away. And then of the remaining part, we take the partial derivative with respect to one of the epsilons, and then we get the factor, this factor in front of here times xn, where xn is 0.1, so that is then easy to get the 1 back. That way we have calculated that this has a 1 and this one has a 1 and so on. And we discovered that this, if you take the partial derivative with respect to C1, then you get something that is not depending on E4 and E5. Why not? Okay, maybe it is me, but it looks different than what we had before. What? Why is it different? Impossible! What the fuck? Yeah, this, okay, all 6, and then we get all of them except E3. And here we get E3 back, but no E4 and E5. Okay, this is not funny. This is not funny. No, it's different every time. So actually it is E0, E1, E2, E3, E4, E5. For all of them. And if we run it again, sometimes one of them disappears. How? Because these are determined from the fact that, well, these are 0. If I have zeros here, then why do I have all of them? I have to go to the shop. I'll be back later, because I have to buy something. In the meantime, please solve this problem here. How the hell can this vary? What does vary? See, now these are the E3 dropped out. Here the E5 drops out. Now they're all back. Now here the E4 dropped out, the E5 dropped out. I'm inclined to think that the correct answer is that every epsilon happens everywhere. That's all right now. But then why sometimes do they disappear?